And here's the answer to the quiz question. And I think this answer is quite straightforward. Should not have caused you a lot of trouble to find out the right answers to this question. And now we arrive at the most interesting graphs of chapter 7. So please pay attention. And the first graph is actually one that we derive from chapter 6. So chapter 6 we did not study, it's not part of the course, but this figure is because it gives you the main insight which you need for chapter 7. So, and we observe that in the left panel we see on the x-axis labor, and on the y-axis we observe capital, and we depict in this graph something that are called isoquants. And just like in difference curves, we give you the consumption bundle that allow you to attain a given utility level. Isoquants are combinations of capital and labor that allow a firm to produce a given amount of output. So here we look at a firm that produces engines, and it uses two production factors in order to produce engines. And these two production factors are capital and labor. So the first graph that is shown is the isoquant. So this is this curved brown line. And this is a combination of all combinations of capital and labor that allow the firm to produce exactly 10 engines. But of course, the firm wants to produce 10 engines at the lowest possible cost because it wants to maximize its profits. So in chapter 6, what is done is to derive which of these bundles that each allow the firm to produce 10 engines, which of these bundles comes with the lowest cost. So the lowest outlay of cost to capital and cost to labor in the form of wages. And to that end, chapter 6 develops something like the iso-cost function, which is fairly equivalent to the budget line that we had in our treatment of consumer behavior. So, and the optimal point, so the green line is an iso-cost line. So these are all combinations of capital and labor associated with a total expenditure of 100. And as with the budget line, the slope of this one is also derived from the relative price of capital, units of capital and units of labor. And the optimal point, so the combination of capital and labor that allows the firm to produce 10 engines at the lowest possible cost, is the point X, where the isoquant is exactly tangent to the iso-cost function. And just like we have an optimal consumption bundle being the point where the indifference curve is tangent to the budget line. So if we want to produce 10 engines, then we do so by choosing an amount of capital and labor as represented by the bundle X. But maybe we want to, and then on the right panel, we can depict it. Okay, on the x-axis here we have the output level, so 10 engines, and then on the y-axis we have the total cost. And we observe from the left panel that if we have an output of 10 engines, then our cost will be at the optimum $100. Of course, we can also do this for different quantities of output. So for example, take what is our outlay if we want to build 20 instead of 10 engines. And we can see that if we then again minimize the cost, so we take the point where the iso-cost line is tangent to the isoquant associated with an output of 20, we reach point Y, certain combination of capital and labor, and there's a price to capital and a price to labor. So that gives us a total cost of production of 180. So it's a little bit less than 2 times 100 in this case. So we can double the output without doubling our total cost. Then we can continue. So what is the optimal combination of capital and labor if we want to produce 30 units of output? It's point C. And at this combination of capital and labor, our total expenditures will be 300. So now another 120 of cost is added if we want to produce an additional 10 units. So, and we can do this for all quantities that we want to do. And then on the left panel, you can connect the optimal points, and you get something that is called the long run expansion path. And you can also derive or connect the dots in the right panel, and you get the long run total cost function. However, but why is this called the long run expansion path? Well, it's called the long run expansion path because in the long run, if you consider a long enough period, then you can adjust freely both capital and labor. So you can sell any machines that you don't need in your plant, and you can buy additional machines if you need them, and you can hire additional workers, and so on and so forth. In the long run, all that is flexible. But in the short period, firms don't have that flexibility. So in the short run, firms cannot always adapt all their production factors. And in our treatment, as we do it here, we often assume that in the short run, you can adjust one production factor, that is labor. So in the short run, you can easily hire additional workers or fire workers that you don't need. But in the short run, you cannot adjust the capital that is in place. So you cannot easily expand your plant from one day to the next or put in additional machines. So the blue line is the long run expansion path and the long run total cost function, but in the short run, your amount of capital is fixed. So there's not much that you can do. Now, how would that work out? So suppose that in the short run, the amount of capital is fixed at 5 units. So we plug in another line in the left panel, which means that in the short run, okay, if you want to produce 30 units of output, ideally you would adjust capital and labor such that you arrive at the optimal point C, associated with a cost of 300. But in the short run, this point is infeasible because you cannot increase your amount of capital. Your amount of capital needs to be fixed at 5, so you can only change the amount of labor. So you can only move along this horizontal line. So then if you want to produce 10 units of output, well, what is the optimal thing to do is you cannot be at point X, because then you would have to adjust your amount of capital. You can only be at the point X prime. So that's the minimal cost at which you can produce 10 units. And at that level, your total cost will be slightly higher than the 100 that we had before. So I don't know exactly what they are, but suppose that they are 120. So, and then you can also do this for the other quantities, like for example, the quantity equal to 30. So you cannot be at a point Z because your capital is fixed at 5 units. So the optimal thing that you can do is to be at point C prime. And at that level, your cost of production is not 300, but again, a little bit higher. So say 360 and so on. And well, given that you, the exception of course is if you want to produce 20 units. So originally you were at point Y, and lucky you, if you want to produce exactly 20 units, then you already had 5 units of capital in place. You don't need to change that because 5 for the production of 20 is exactly optimal. So the point Y stays where it is. That's the point that is still feasible because it's the point associated with 5 units of capital. Now, connecting these dots gives you the short run total cost function. And on the left hand side, yeah, this is called the horizontal line, the short run expansion path, because the capital is fixed at 5 units. And the important thing to note is that the short run total cost function is identical at one point, but mostly above the long run total cost function. And of course, This needs to be true by definition, because in the long run, you get one extra parameter that you can change. In the long run, you can change capital. In the short run, you cannot, and that's the only difference. So given that you are more flexible in the long run and you want to maximize your profits, the total cost of the firm, if anything, must be lower in the long run. So that's a lot to say about one or maybe two graphs here. And the story continues. So chapter 6 introduced two production factors, labor and capital. And in the short run, the amount of capital is fixed, which means that the short run total cost curve describes total cost while keeping capital fixed. So and for the same reason as before, the short run average variable cost cannot be lower than the long run average variable cost, because the only difference is that in the long run you can also adjust capital to your favor, and that will mean that the long run average variable cost, if anything, is lower than the short run average variable cost. And that holds for every average variable cost curve, each of which corresponds to a different capital level. So we keep that fixed, but in the long run you can adjust it. So in the long run, the cost of producing the given amount of units, if anything, the variable cost must be lower than in the short run. And this implies that the long run average total cost curve will envelope all short run average total cost curves. So in the long run you can also adapt capital to your benefit, so you can have a lower fixed cost. So that means that the long run average total cost will envelope all short run average total cost curves. Now this concept of enveloping can be quite difficult, so it's good to do it graphically. What does it mean? So here's the graph, and this one is also not that easy to read. But focus on the x-axis, which has the quantity of engines again, and the average total cost, so the cost per unit, is on the y-axis. And now suppose that we have the optimal amount of capital in place to produce 20 engines at the minimal cost. So then in the short run, given that amount of capital in place, the average total cost reaches a minimum at the point y, which is the same point y as in that we observed 2 slides before. So given the amount of capital in place, we have the optimal amount in place to produce 20 engines at the lowest average total cost. And so to denote that's why the 20 is here in the index. So that's in the short run the lowest cost at which we can produce 20 units of output. Still focusing on the short run, so we can adjust labor, but we cannot adjust capital. What if instead we produce 10 engines or 30 engines? So this is what is said. So the cost is 9, capital is optimal for producing 20 engines. But now, if instead we don't produce 20 engines, but only 10, and we cannot adjust capital because we're in the short run, then the average total cost will be X prime over here. So it will be $12 per unit. And of course, that total cost is higher than what we would be able to obtain in the long run, where we can adjust the amount of capital to the lower number of engines, for example, by selling some machines. So in the long run, we might be able to adjust our capital such that we could produce at the level X. So this curve gives you the average total cost curve associated with amount of capital, amount of machines in the plant that is optimal, so cost minimizing to produce 10 units of output. So in the short run, when our plant is equipped for producing 20 engines, we cannot adjust capital. So our short run average total cost will be $12, but in the long run, when we can adjust it, it will be slightly lower. So in the short run, with again the amount of capital in place being okay for 20 units, but a little bit too little probably to produce 30 engines. So if we want to produce 30 engines in the short run, we cannot scale up by increasing capital. So we have to do it by just having workers working overtime or something like that. That's the only way that we can produce 30 units, but it's more costly than the long run solution. So the short run solution will bring us at the point Z star or C prime, also associated with an average total cost of production of 12. In the long run, we can buy some extra machines, so we don't need to hire extra workers or pay them overtime hours. So in the long run, our average total cost, again, may be cheaper. And this is the average total cost curve associated with conditional on having the number of machines in the plant that's optimal for producing 30 units. So for a given amount of capital that is fixed and is optimal for 20 engines, this is the short run total cost curve. But in the long run, when we can adapt capital, then the cost of producing 10 or 30 engines will be lower. And of course, we can do this not only for producing 20, 10 or 30 engines, but for all number or quantity of engines. So and then we can connect all the minimizing points and we get the long run average total cost curve. And as you can see, the long run average total cost curve acts like kind of a bowl around the short run total cost functions. So it envelopes the short run total cost functions. And that is what is meant here. That's the story behind this graph. One thing that you may ask, and this is really the good question to ask to see whether you really understood what is done in this picture, is to say, hey, but here the long run average total cost curve touches upon the short run average cost curve at the minimum point, but here it is tangent at point C and it doesn't touch upon the minimum point over here. Why not? Well, this cannot be, because now suppose that the long run average cost curve would intersect with the minimum point of this average short run total cost curve. Well, that would mean that it is intersecting. So at some point, it would run through the average, the short run average total cost function. So it would mean that after the point of intersection, the long run average total cost function would be above the short run average total cost function. And that cannot be, because in the long run, we have more flexibility than in the short run. So the long run total cost curve can never be above the short run total cost curve. And this is what you would automatically get if you would have this long run total cost curve not to be tangent here, but to be intersecting with the minimum point over here. So I think I have this graphically here. So suppose that it would intersect with the point C double prime, then the long run average total cost curve would look something like this. And clearly it would be above this short run average total cost curve that we have over here. And by definition, long run more flexibility than in the short run, so the long run cost cannot be higher than the short run cost. Okay, so this was a short but intense episode with a couple of graphs. And then to finalize this, the short run marginal cost is the cost of producing an additional unit when capital again is fixed. And the long run marginal cost is the cost of producing an additional unit when both capital and labor can be flexibly adjusted. So it must be that the long run marginal cost curve will be flatter than the short run marginal cost curve, for the same reasoning as we followed before. Now we can bring this into our picture. So we have the average cost and the marginal cost here on the y-axis. Again, the quantity of engines on the x-axis. So the average total cost, which is optimal for producing 10 engines, is given by this one over here. This again is our average total cost curve. That is when the optimal amount is in place for producing 20 engines and the one for 30 engines. As we know from what we had before, in the short run, the marginal cost curve intersects with the average cost curve at the minimum point. Think of having a grade average of 7. If your next grade is higher than 7, then the average grade must increase. If it's lower than 7, it decreases. Same for the average and marginal cost. And we have that in the long run, the marginal cost of production must be lower than in the short run. So it must be flatter. So here you're at the optimal point. In the short run, you cannot adjust your capital. So if you want to produce more than 20 units, the marginal cost is pretty high. In the long run, the marginal cost curve is much flatter. So it's because you can adjust capital, which allows you to produce incremental units at a lower cost. So in the marginal cost curve intersects the average total cost at its minimum. That's something that we have, and the long run average cost curve intersects also with the short run marginal cost curve at the optimal production output level. So these are the points A, Y, and B. And for example, this B over here is the point where the short run marginal cost of producing an extra unit is exactly, for at least a short period, equal to the long run marginal cost of producing extra amount of output, and that is the point that is consistent with the point Z star over here. Okay, so and that brings us at the quiz of this section. And the quiz is, suppose that the firm has a production function Q is K L to the power 0.5. So you plug in a certain units of capital and labor that you have in place, and what follows is the output Q. The cost of capital is 60, the wage rate is 30, and the short run, the amount of capital is fixed at 100 units. And then the questions are, what is the short run production function? What is the short run demand for labor? And what are the firm's short run total cost and short run marginal cost? So, and in the short run, K, the amount of capital here, is fixed at 100 units. And here's the answer to the quiz question. So already in the introduction to the question, I told you that the production factor capital is fixed at 100 units, and that you need to plug in this value of 100 in the production function. So then you have the output as a function of the units of labor that you use only. And you solve for the number of units of labor to get the number of units of labor as a function of the output that you want to attain. So doing so, you have the square root of L is Q over 100, and then taking squares at both sides, you have that the number of units of labor is the number of units of output squared over 10,000. And that solves A and B. And then to arrive at the total cost in the short run, with capital being fixed at 100, the total cost is the cost of capital. So the unit cost of capital is equal to R, which is given to be 60. In total, we have 100 units of capital. And the total cost of labor, well, the number of units of labor as a function of our output level Q is Q squared over 10,000. The cost of 1 unit of labor is 30, so we multiply with 30 and we arrive at the total cost function, short run, of 6,000 plus 3q squared over 10,000 or over 1,000. So 30 over 10,000 is 3 over 1,000. To arrive at the short run marginal cost function, we take the derivative of this function with respect to q. So that gives us 6q divided by 1,000. And as you can see, this is a positive function which is positive in q. So the short run marginal cost increases as the output q increases. Now, we have a short remaining part of chapter 7. So what happens to the long run average total cost as a firm grows? We distinguish between a couple of situations. So we have economies of scale when the cost rise more slowly than production. So we've seen this example at the start where you increased production from 10 to 20 units and your total cost increased by from 100 to 180, meaning that you could double your production without doubling your cost. So then you have economies of scale. The flip side is that you have diseconomies of scale when the costs rise more quickly than production. So for example, you double your production, but that then more than doubles your total cost. And the very borderline situation is where you have exactly constant economies of scale where the costs rise at the same rate as output. Notably, this is not the same as returns to scale and when we talk of returns to scale, we only consider the production technology and not the cost of producing output. Whereas with economies of scale, we can also vary the units of capital and labor that we use. Graphically, suppose that this is our average total cost function, then when we're in the low regions of quantity, we have economies of scale. So we increase production and our average total cost is decreasing. So economies of scale. But once we reach the minimum point, our average total cost start increasing again, meaning that if we further increase our production, then the average total cost of production, they go up and we have diseconomies of scale. And then we have this one point where we have constant economies of scale. And that brings us to the end of chapter 7. So what we did in chapter 7 is that we looked at production factors in output and linked them to the cost of production. So we looked at different cost concepts like opportunity cost, fixed cost, variable cost, sunk cost, marginal and average cost, short run cost, and long run cost, where importantly, in the short run, we often assume that the amount of capital cannot be changed. That is fixed, whereas we can tune with the amount of labor that we use. In the long run, we can change both flexibly. And in the next chapters, starting with chapter 8, we introduce the market conditions to the firm's production decision. So in chapter 7, we only looked inside the firm, what happens inside the firm, only taking the cost of the inputs, capital and labor into account, but no further market exposure. In chapter 8, we're going to consider what happens if the firm enters the market and is also confronted with the price that it can get for its output Q. And we do so starting with the market of perfectly competitive market, because that is an extreme situation, but it's also a very easy situation to analyze because we abstract from any strategic interaction between firms. So that will be coming up next.